I'm Lauren Bennett, and these are my colleagues, Flora Vale and Janora DaCosta. The three of us, we all work on the spatial analysis development team. Myself and Janora work on the spatial stats tools, which you'll be seeing a whole lot of today. Flora is kind of an honorary member of the spatial stats team, but also works on getting charting into ArcGIS Pro and ArcGIS Online and everywhere else that charting is necessary, which is everywhere. But she is on the spatial analysis team and definitely part of our team. So this morning we're going to talk, this is our most ambitious session. It's really ambitious. So our goal is to talk about every single spatial stats tool. There's a lot of spatial stats tools. So we're going to demo a lot of them, not all of them, because we found out yesterday we can't demo them all in one session. We found out the hard way. But what we are going to do is talk about all of them, and we'll go through and kind of point you to some places where we'll talk a little bit more in depth about some of the other tools that maybe we aren't going to get as in depth into as we would like to. And we're going to have some fun. So let's get started with what are spatial statistics. So spatial statistics, if you looked up in the dictionary, what are spatial statistics, you'd find something that says that it's a set of techniques that allow you to explore spatial patterns and trends and relationships that exist in your data. Now, that's kind of a boring academic definition of it. Just reading that, I'm not sure anyone would even be here right now. But that's okay. One thing that I do think is kind of important to note is that these are not just traditional statistics that we happen to apply to spatial data, right? We're not just taking traditional statistics and throwing our spatial data at them and hoping that they're useful. We're actually incorporating geography into the mathematics. Geography is a critical component of spatial statistics. And so the way that kind of geography rears its head in all of these statistics is through things like coincidence, orientation, length. Proximity is one that's really, really common. One of the most common ways that we kind of integrate geography into spatial statistics is by thinking about how things are related in space, whether it's by proximity or it's by, our boundaries touch, that kind of being near each other. But really, a big chunk of what spatial statistics have at their foundation is Tobler's first law of geography, right? Things that are closer together are more related than things that are farther apart. And that, as its foundation, is kind of what spatial statistics are built around. But all of that is really just a lot of words to say that the truth is that spatial stats really just extend what our eyes and our mind do naturally every time we look at a map. Spatial stats are just doing what our brain's really good at in the first place. So every time we look at a map, it is virtually impossible for a human being to look at a map and not start finding patterns, right? You look at a map of points, oh, I see a clump over here. It looks like it's a little darker over there. What's going on up here? Oh, I know that area. I can not only see that there's a clump, but I know why. We do this. We not just find patterns, but we also start to at least think we understand relationships, right? Now, the brain is an incredibly powerful statistical tool. It is basically the most powerful statistical tool that exists on the planet. But as good as we are at finding patterns, we're also really good at finding patterns that aren't there. And it's dangerous often for us to be doing this, right? So that kind of visual analysis where we just look at a map and say, oh, I see the patterns, I see where it's dense, I see where it's light. We are easily biased by our own experiences. So that can be very powerful. It can help us find connections, but it can also lead us down paths where we're spending resources that are already limited in places where we're not going to get a lot of impact So that really brings us to this idea, this question. Are you using data or are you using information? And I think we're seeing a lot of this these days. I think it's particularly coming up because we have so much data now. We're like inundated with data. And there's this idea that you can be data rich and information poor. And I think that's happening because we kind of, if you think about a spreadsheet, I don't think anyone in this room would disagree with me when I say, if I showed you 100,000 records, do you have data or information? Data, right? No one's going to make a decision looking at 100,000 records in a spreadsheet. That is ridiculous. So what about a map? So you put your 100,000 records on a map. Is it data or is it information? I love that some people are throwing out data. That makes me happy. Because I would say when we put our data on a map, I think we do put one foot in information. But we leave the other foot very firmly planted in data, right? We start to uncover things in our data that we wouldn't have seen in a spreadsheet. We start to understand patterns, again, with a visual analysis that could be totally made up in our brains. But we do start to uncover patterns. If you've never seen your data on a map, seeing it on a map is very powerful. But we are still asking our brain to make sense of 100,000 points on a map. And it's still it's asking just a little bit too much of our brains. And so with spreadsheets, we do things like get the standard deviations, the mean, the min, the max. You do very simple descriptive statistics to start off with, right? And then you go from there into all sorts of different kind of analytical things that we can do to understand that numeric data better. But the same thing goes for maps. We can do more, and that's what spatial stats are all about. They're all about being able to quantify the patterns that we're seeing, quantify the relationships that we're seeing, and really understand those patterns and those relationships and be able to trust and have confidence that it's not just our brains tricking us. Now, I do want to point out before we kind of jump into it, we're going to be talking about the Spatial Stats Toolbox. It's a lot of tools. It's going to be a whirlwind tour, okay? Like buckle your seatbelt or whatever you're going to do, but strap in because it won't be a bumpy ride, but it's going to be fast. I do also want to point out that most of these tools have a little script next to them, and that means that they are Python scripts. Now, the fact that they're Python scripts is pretty cool for a couple of reasons. One, you can right-click on them and hit edit and open up that source code, which means these are open tools. Anyone can look at them. You can dig into the math. In a lot of cases, we document the paper or set of papers that are the underlying kind of foundational seminal paper for the tool that you're looking at. If you're getting into Python, they can be a powerful kind of set of examples for how you can use Python to implement some pretty sophisticated analytical functionality using Python. We don't have access to some special library of Python that we use to build our Python tools, and then you guys use some other library of Python. We are using the exact same Python libraries, ArcPy, that you have access to build your own kind of advanced tool. So if you're getting into Python, because it is kind of the way to extend the analytical capabilities of our software, these can be great examples. So with that, we're going to start with the measuring geographic distribution tools. This is one of the tool sets in the toolbox. And really, you can think about these as kind of a parallel to some of those descriptive statistics that I mentioned that we start with when we look at a table, right? Our mean, our standard deviation, our min, our max, that sort of thing. So we're going to get started with the first tool, which is a tool called Central Feature. So Central Feature, it's a pretty simple tool. It essentially chooses one of the features in your data set that is the most centrally located. So one of the features that exists in your data set is most centrally located, and that's what we're looking for. And so what it does is it measures the distance from each feature, right, to every other feature, goes through, and then it adds those up. And the one that has the shortest distances, when all summed up together, from each feature to its, from itself to its neighbors, that's the most centrally located feature. And we pick that feature as the central feature. Now, it seems like a really simple tool, and it is, from a mathematical standpoint, but you can do some pretty sophisticated things with it. So Janora is going to give us an example of how we might use central feature.
All right, so what we're looking at here is are all of the fire stations in Fort Worth, Texas. And we are going to relocate the battalion chief's office to the most centrally located fire station. So we're going to open the central feature tool. And so this is pretty simple. I might, just looking at the map, might choose one of these. They look kind of like the most central. But let's find out which one is the best. So we're going to input active stations. And then we have some options. We can choose how we define distance. I'm going to choose Manhattan because it's based on right angles. And then we can also use the weight field. So I'm going to weight each fire station by the number of employees that work there so that those that have more employees will pull the central feature. And we'll click OK. And this is taking a little bit longer than usual. Interesting. Let me try that one more time. Oh, no. So the answer, it actually chooses station 5, which is oh no.
The good news is that Murphy's Law requires that happen, and we've got it out of the way right now.
Perfect.
So that's central feature. It's magical, yes. Very impressive. It's okay. So you get it. It's a very simple tool. But I mean, something like locating a fire station, it's a great example where you're not going to build a new fire station at the most central location of your data. You're going to pick one of your existing fire stations that's already there. You're not going to build a whole new one just to put the chief in the most central location. And so picking, having a tool that helps you find that is very powerful. So the next tool is the mean center. I would say this is probably the simplest tool in the toolbox. But it is one of my favorites because it's really simple. At least the concepts behind it are one of my favorites because understanding the centrality, the kind of that part of your data, I think about it like it's boiling my data down so that I can make sense of it. So the mean center, essentially, we have a bunch of XY coordinates, and what we do is we add up all of our X's, and we add up all of our Y's, and we get a mean for each of them. And then we put a point at that location. So you could do this math by hand if your coordinates were very neat and integers like these are, and you'd be able to calculate the mean center yourself. Of course, usually they're not quite this neat, so it would be a little bit tricky. You probably would want a calculator. But it's a very simple kind of mathematical computation, but at the end of it, we get this picture of what's centrally located in our data set. So Janora's going to give us show us an example of using the mean center.
Yeah. All right. Okay, so here we are looking at population in California, and some of the most powerful ways to use these simpler tools are actually, we could run mean center once, and we will do that, but another powerful way to use this tool is comparing distributions and how they may change over time. So I just ran this while we were over there, so this one will work. So I'm going to input my population data from 2010. I'm going to weight it by population and run. There we go. And it's not surprising that the mean center of population in California falls somewhere between Los Angeles and San Francisco. So what I've actually done is run mean center for every decade since 1900, and I am going to animate the results by creating a group animation. All right, and we can see, let me play this one more time. We can see the mean center over the last century has moved significantly down from San Francisco to Los Angeles, and that's reflecting when people were moving to California during the gold rush, and then the shift in population down to Southern California as LA grew and Hollywood became famous and things like that.
Yep, and one of the things you're probably thinking about right now is how awesome mean center is, but then also, wow, that animation's really cool. So we show the animation. We show you how to make the animation because when we started doing this, we would just put an animation on, and everyone thinks it's magical. And so at the end of it, we'd give a whole workshop on like the things we work our fingers to the bone to build, and then the first question is, how did you make the animation? So we avoid that question altogether. It's drop down. The animation is just a toolbar, and you can make a group layer. So as long as it's in a group layer, it just goes through and turns one layer on at a time, which is really great because Janora is absolutely right that being able to use these tools to make comparisons, either over time or between different sets of features, is very powerful, and that's when they really are the most powerful. Just looking at the mean center of population in California might not be that interesting, but looking at how it's changed over time, then we're really talking about something powerful. And I think if you think about looking at that map for population in 2000, the traditional way to do this without something like a mean center, we'd look at the map for 1900. 1910, 1920, 1930, 1940, get the drift, right? Does anyone, I mean, you don't remember what 1910 looked like by the time you get to 2000. So being able to boil that pattern down into these mean centers and just watch them travel is very powerful. So the next tool is the median center. And median center is very similar to mean center, except it's a median, right? So again, we have a bunch of XY coordinates, and instead of adding them up and calculating a mean, we order them in a line and find the median. And we put that location right where it falls. Often it will be very similar to a mean, but not always, which we'll talk about in a minute. And Janora's going to show us how we might use the median center.
All right, so this time we are going to cite library satellites that are not just for reading, but also provide internet access to this community that has very low internet access at home. So I'm going to open my median center tool, input my patron locations. No, there it is. Okay. And I'm going to use the case field this time because we're not going to locate just one library satellite. We're going to locate 3. We're going to locate 1 per district. So I'm going to input my, not the usage field, the district. So each patron location has a field on what district they are located in. So what the case field is going to do is median center is going to go through that field, and for every unique value, it's going to group those together and then find the median center of that group. So it will take all of the patrons that are in District 1 and find a median center there, and then so on. And here we have 3 median centers.
And so that case field could be a text field, it could be a date field, it can't be a double because that would be kind of crazy, but it can be an integer, a date, a text field, and it's just a great way to kind of, if you have, especially because they are so valuable from a comparison perspective, we have the case field there because it helps you make those comparisons, right? We see where they are for each district. We might have used the years in a data set and calculated one for each year, that sort of thing. Okay, so we talked about mean and median, but of course, like most analytical tools, oftentimes there's more than one way to, it's a terrible saying, skin a cat. I love my cat. There's got to be a better saying than that. You get the drift. There's a lot of ways to do the same thing often, and they all have little nuances why one might be better under certain circumstances. And with the mean center versus the median center, it's very similar to what you would expect. It's very similar to the reasons for just a regular old mean and median, that we would choose one versus the other. So if we take our same point data set and we think about adding in a crazy outlier, a spatial outlier way up in the corner, right? If we recalculate our mean, that one outlier dramatically changes our mean, right? Now, if we do that with a median, it doesn't change it much at all, right? Because we're just adding one value on either side of our ordered list. So the mean is very, very sensitive to spatial outliers, whereas the median, much less sensitive to spatial outliers. Now, there's pros and cons even within this. Medians are actually, from a computational standpoint, harder to calculate because you have to create this ordered list. Means are easier to calculate, they're faster. So that's more on our side of things, having to deal with the computational challenges of median and implementing it in various places. But thinking about if you have spatial outliers and how much they matter, and sometimes you want those spatial outliers to pull your mean, right? You want the mean to truly represent the distribution of all of that data, including those spatial outliers, but sometimes you don't. And so using them, having that in mind is important. So far we've really been talking about data that applies to, or tools that could apply to points, lines, or polygons. These tools work for points, lines, and polygons. If you use polygons, we use the centroid of your polygon. But we saw in the population example that Janora showed that if you have an attribute associated with those polygons, it can still be interesting to run some of these analyses if you're weighting by an attribute field. Linear directional mean is really all about lines. It's looking for the average direction, the average length, and also the geographic center of a set of lines. So here we have a set of lines, and basically what we do is we calculate the kind of directionality in those lines, and we come up with this linear directional mean. And this can be powerful. We've done analysis on, for instance, car theft. And we looked at where the car was stolen and where the car was recovered to see what was kind of the linear directional mean of these car thefts, which was just an interesting kind of way of looking at that data that we wouldn't be able to see if we just looked at a bunch of lines or even just a bunch of points of recoveries and thefts. Janora's going to show us another example of how we could use linear directional mean.
All right, this is one of my favorite maps because it's so useful. These are paths of hurricanes that have occurred since going back all the way to 1851. So I'm going to try to boil this information down. Open the linear directional mean. I'm going to input my hurricane tracks. And then I'm going to use the case field again because I don't want just one average of all these lines. I'd like the average per year so we can see maybe how the trajectories have been changing over time. So I'm going to input my year and run the tool. This is actually 38,000 hurricanes, and the tool is running actually pretty fast considering the amount of data it's processing. And there we go. And so now we have all of these arrows, one per year since 1851, and I'm just going to re-symbolize this really quickly. All right, and I'm going to overlay that onto the arrows. So we can see that the lighter arrows are the ones that happened closer to 1851, and then they get darker over time. So you can kind of, you still can't probably like make any conclusions from this map, but you can kind of see the darker arrows are, towards the right side of the map and the lighter ones towards the left. So we boiled down the information into bite-sized pieces.
Well, and I think one of the things that we talk about a lot, especially when it comes to some of these measuring geographic distributions tools, is that it's very rare that we've seen some examples, you're citing where you're going to put these kind of mobile internet facilities. That's a great example of something where you have a very simple question. The answer is very simple. But oftentimes, these measuring geographic distribution tools are not going to be the answer to your question because your questions are big and they're complex. And so most of the time, they're going to be a place to start, a place to begin exploring your data. I don't know about you, but for myself, I often get a big data set and I have a big question. And that big question usually doesn't have a single tool that I can run that's going to answer it, right? It's not like the magic button, the easy button for the solution to my problems. Someday that may exist. For now, we're forced to figure out how to break our problem into bite-sized little pieces that we can then follow a process of analysis to figure out how to solve our problem. And oftentimes, we don't even know where to start, how to begin breaking that problem down into its pieces. And so the measuring geographic distribution tools, if you think about with the hurricanes, instead of having what is a completely useless map of green, a sea of green, now we have at least some patterns that we can start to look at so we can focus our questions a little bit further. Is there a pattern at all? Maybe the pattern hasn't changed, but then we know over the last 150 years, the pattern of hurricanes hasn't actually changed. The linear directional means haven't changed. Or why do we see that they've shifted? Maybe to the east. So we have ways, these are tools that we can use to explore our data and kind of guide the analysis process. It's very rare I get a data set that I don't start exploring it with some of these tools. So the next tool we're going to talk about is standard distance. It's essentially a way of measuring how concentrated or dispersed our data is around a mean center. And so what we end up with is kind of a picture of just how concentrated or dispersed the data is. It gives us, if we had a really big coverage around our study area, we'd have very dispersed data. If we have very, very, very tight little circle, we'd have very kind of concentrated data. We're not actually going to show you the standard distance tool. It is powerful, but I would argue this one's more powerful. The directional distribution tool, standard deviational ellipses, it's similar in some ways to standard distance, except we get even more information. So it's centered on the mean center, so we get a picture of its central tendency. We get a picture of its dispersion or concentration, and we get a picture of directionality. And so what we end up with here is an ellipse that covers either 68% of our data, which is one standard deviation, 2 standard deviations of our data, which would cover 95%, or we cover 99%, which is 3 standard deviations. So we have this way of seeing exactly how, if there's a directionality in our data, where our data is centered, and the dispersion or the concentration. And since this kind of encompasses a bunch of different things, including mean center, I would say this is the tool that I always run when I get a set of data, because I can immediately start to boil down that data a little bit further and start to make sense of it. So Janora is going to show us an example of using the standard deviational ellipse tool.
All right, so this is Ushahidi data in Libya, and what you're looking at points on the map where people have requested humanitarian assistance via SMS. So one thing that we could do is maybe just do an animation where the points like turn on and off over time. That might be interesting, but like Lauren said, we can do more. So I'm going to run directional distribution, input my Ushahidi data. And I'm going to use the case field again. So what I've actually done is group all of the requests from week 1, week 2, week 3, all the way through week 9. So it will give us a directional distribution of the requests for each week.
If you had really dense data that was coming in, like tons of data day to day, you could use the date field. But in this case, the data is kind of sparse, and so clumping it week to week really made the most sense for what we were trying to do. You also run into the issue that if you're looking at a lot of data, this was 9 weeks worth of data. If we did have a lot, looking at it daily might still not make a whole lot of sense, because we're going to end up with probably too many ellipses, right? So kind of thinking about the scale temporally of how you want to ask the question, in this case by week, made a lot of sense for us.
Okay, so it's given me 9 ellipses, one for each week, and I've actually gone in and re-symbolized them a bit, and I'm going to do another animation. And you can see, so week 1, week 2, where did it go? There it is. It gets smaller. And we can see how not only the pattern, but the direction is slightly changing over time. So as Lauren mentioned, this is a great tool. It's actually her favorite tool. But we all, this is one of the first tools we run whenever we see new data, because it is so exploratory. And at first, our question is, what is going on with these points in the map? But now our question is, why is this distribution changing over time?
And even as far as to say, what happens between week 8 and week 9, that we see such a big shift in what's going on. And we can export in the animation dropdown, there's an option to export this to an AVI file. Send an AVI file to someone who has no idea what GIS is, they're going to understand those ellipses changing over time, right? It's very kind of simple to understand, which is another part of kind of the power of these tools. In their simplicity, they're actually incredibly powerful because everybody will get it. And there's a lot to be said for kind of using, and I kind of always harp on this a little bit, but I think we have a tendency to want to use the most sophisticated analysis tool we can possibly think of, right? Even if we don't need to solve our problem. When in reality, the simplest tool we can use that solves our problem is the best tool to use. Because getting more complicated is just getting more complicated. And it means it's going to be more difficult to explain, more difficult for leadership or decision makers to get behind and understand. And in a lot of cases, you're introducing a lot of room for that complexity to kind of drown out and make things less clear than they would have been if you stuck with the more simplistic. It's this idea, it's kind of Occam's razor. It's also kind of the idea of parsimony, right? The simplest way we can say things is the best way to say them. I mean, if you can't say it simply, you got to get complicated, right? But sometimes we overcomplicate things kind of unnecessarily. All right, so moving on to the next tool set, which is analyzing patterns.
We should switch so that
And Laura is going to talk about analyzing patterns. It is musical. Chairs, product engineers.
Oh yeah, I forgot that you were, that's why I took your microphone, sorry. All right, analyzing patterns. This tool set is actually what inspired me to want to do a workshop where we talked about every single tool, because I realized that I didn't completely understand what these tools did because we never really talked about them. And I realized that you guys probably don't know either. And so I'm going to go through these, but they do tend to be a little bit more academic. All of these are looking for degrees of clustering, but they just all do it in different ways. Like Lauren said earlier, many ways to do the same thing. So we'll explore these. And now we're going into inferential statistics. So we're going to get a probability that tells us how confident we can be that the data exhibits clustering or dispersion. So the first tool, average nearest neighbor. How average nearest neighbor looks at clustering is that for each feature, it measures the distance to that feature's nearest neighbor, and then it finds the average distance, and then it compares that to an expected average distance. And so there's a ratio. The observed distance divided by the expected distance. If that ratio is less than 1, then the data exhibits clustering. If it's more than 1, then the data is dispersed. So we're not going to demo that one. With all of these tools, you get back a probability of confidence, how confident you can be that the data is exhibiting clustering or dispersion. And so oftentimes these tools are best used for comparisons. So you can compare the same place over time, or you can compare two different locations to see which one is the most clustered. But by itself, just the one number doesn't necessarily give you that much information. Next up is spatial autocorrelation. And this one we actually use probably the most often out of this tool set. And again, it's looking at the data to see if we have clustering or dispersion in values. So are the distances and values correlated? And that was a little bit confusing to me, so I did some research and I illustrated the point here. So we have values and locations. So we have distances in location, like 14 is 20 kilometers away from 32, and 14 is 3 kilometers away from 16. But then we also have distance in data space. So 14 is 18 away from 32, and 2 away from 16. So we're looking for a correlation in those numbers. As the features get farther apart, do their values become more similar or less similar? If features that are close together have similar values, that is clustering. If features that are close together have very different values, that's dispersion. So we will actually do a demo of this one. Janora will.
Okay, so we're going back to the California population data. I'm going to open the tool, input my 2010 population, and generate a report. All right. And I can go open that tool, open the result, and see that, so the output is a z-score and a p-value, and we can see right here that this data is clustered. We give you a picture, we give you the numbers, we give you a sentence down here at the bottom. But as Flora was saying, some of the most powerful ways to use this tool is by comparison. So what I've done is actually run spatial autocorrelation for every decade, and I have a open. And I have a table here with the year and z-score for every decade. And what I can do with that is create a graph. And we can very clearly see that in 1900, the z-score was 2.6. And we can see over time that there was this decrease happening in the intensity of clustering until around 1930. And then in 1940, the intensity of the clustering starts increasing again.
Okay, so that was spatial autocorrelation. Next is incremental spatial autocorrelation. So incremental spatial autocorrelation is actually just spatial autocorrelation run over several distances and then charted. So similar to how Janora went through and created a graph of z-scores over different years, incremental spatial autocorrelation runs spatial autocorrelation at different distances, and it plots the z-score at each distance to find a distance at which clustering is the most intense. And this is how we find a fixed distance band for the hotspot analysis tool. So for lots of those tools, we need to conceptualize spatial relationships, determine what a neighborhood for a feature is. And back in the day, Lauren used to have to run spatial autocorrelation over and over and record the z-scores and make her own chart. So she had our developer develop this tool for her. And now we don't really need this one as much anymore because it's built into the optimized hotspot analysis tool. But it's still there.
And the idea here is the reason that what we're talking about when we say distances is when we look, a lot of the tools that we're going to talk about in the next section are all about looking at a feature in relation to its neighborhood and comparing that neighborhood to, let's say, a global average. And defining that neighborhood is very important. And at different scales, depending on how you define that neighborhood, you're asking different questions. And so what this is looking at is how intense is the clustering depending on how I define my neighborhood. And it's looking for a scale at which the intensity of clustering based on that neighborhood size is the most pronounced. So if you're not really sure what a good neighborhood size is, this is a good way to kind of figure that out. But the idea of at increasing distances is all about we're increasing the size of our neighborhood essentially and evaluating how intense the clustering is at each of those scales.
The next tool is high-low clustering. And this one, I have to admit, I don't think I've ever actually used it. With all of these tools in this tool set, they're global statistics. So they give you one number, one result for the entire data set. So this tool is looking to see if there are high-value clusters or low-value clusters. And it will just tell you, you have very strong high value or you have very strong low value. But if in the data set you end up having clusters of high values and clusters of low values, they're going to cancel themselves out, and it's going to tell you that there is no clustering, which is not true. So you might want to consider
Spatial autocorrelation.
or hotspot analysis, where you would actually get to see where the clusters are taking place. But the way that this one works is that instead of looking at, with spatial autocorrelation, it's looking at the difference in value as correlated to the distance in space. This one is looking at the product of the values as correlated to the distance in space. So if two very large numbers are added together, that's going to be a very large value. And if they're close together, that means it's a high value cluster. If they're farther apart, then it's not. And if they're very small numbers and their product, when you add one to the other, is very little and their distance is short, then that's a low value cluster. Next one is multi-distance spatial cluster analysis, or Ripley's K function. This one is also looking at spatial clustering by distance, but it's actually just looking at the clusters of the location. So most of these other tools are looking at clustering of values associated with locations, but this one is just about location. So it's usually used more for environmental studies to see if a feature being somewhere attracts other features or repels them. So if my standing here is going to attract other people to be near me or repel people away from me.
I have no comments on that.
So the way that it works is we have what we would expect to see and a confidence envelope, and then we look at what we observe, the observed line. So when it's above the expected, that means that we're seeing clustering, and when it's below the expected, we're seeing dispersion. And I was a little bit confused about how can the same data set be clustered at some distances and dispersed at other distances. So I did a little bit of research and illustrated that for you as well. So let's say that this is my data set. If this was my study area at this distance, those are dispersed. They're very evenly spread out. But at this distance, that's a cluster. So that's what that means. And we have wrapped up our academic tool set. Now that you guys know what it is, you can choose to use it or not, but we did promise to talk about every single tool. So.
Well, the spatial autocorrelation tools actually have a lot of use, but there's definitely some. The global, it's funny, musical. Product engineering microphones. No. Actually, to be fair, we didn't ask for 3 microphones until we got here, which is too late. But Lauren Scott, who originally wrote all these tools, was defending her dissertation, and her committee was like the most ridiculous committee of people, including Mike Goodchild. I'm pretty sure it was just a ridiculous committee of like the most famous geographers. And Mike Goodchild asked her if it is even interesting to answer the question, is my data clustered? Because we know, and do not misinterpret that question as him thinking it doesn't matter. He was just asking a question to see how she would respond. And I think she nailed it, of course, because she's awesome. But her response was that, yes, of course, there's some obviousness to that question, right? We know that things cluster together. People cluster together, businesses cluster together, animals cluster together, things cluster. Types of trees cluster together. We just know this. But being able to quantify the degree to which things cluster and being able to do things like compare things over time or compare different distributions and how clustered they are. We know trees cluster, but do some certain species cluster more than others? Now, that's a question that isn't quite so obvious, right? And so, yes, there is an obviousness to the question, but it's all about how you ask those questions. And there are very useful ways to use these tools to answer some of those questions. All right, so mapping clusters, which we will all admit is definitely our favorite. Oh, I have to use your slides. Oh, here, no. Okay, sorry. So mapping clusters is arguably our favorite tool set. We love the tools in the mapping clusters tool set. It's also probably some of the most used tools that we work on because it answers some really useful questions about where clustering is happening in our data. Instead of just asking, is there clustering, it's actually asking, where is the clustering? And so that's for a lot of them. There's also some tools that aren't quite as kind of specifically about spatial clustering in the way that we've been talking about it yet, and we're going to talk about some of those first. So the first one that we're going to talk about is a tool called Similarity Search. Similarity Search I could read this, but the definition's not nearly as useful as just explaining it with an actual example. So imagine you have a bunch of potential store locations, places that you might want to put your next store. And you have the location of a store that is already doing really well, a high-performing store. So for each of our potential store locations, we have a bunch of attributes. Let's just say we have population density, income in that area, the distance to competition. And for our high-performing store, we also have those same attributes. Now what we want to do is we want to rank our potential store locations by how similar they are to our store that's already doing really well, based on however many attributes we think are relevant. So the end result is that we rank those locations, and the idea is, if it's not broke, don't fix it, right? We know what it looks like for a store to do well. We have a lot of good reason to believe that if we put another store in a location with similar characteristics, it may also do well. Assuming, of course, we pick characteristics that are relevant to why that store is doing well in the first place. One of the other ways that this tool could be used, it came up a lot when we were kind of deciding to build the tool, was in community development. So community development folks were asking us for a way to kind of find similar communities to their own so that they could then benchmark themselves against those communities. So the idea being, I'm a small town, I'm a city, like Redlands, let's say, and I am trying to attract new business. And a new big store is thinking about building in Redlands, but it's thinking about a couple of other cities too. And I want to convince them Redlands is the place to build, right? So I'm going to say, hey, we're just like these 5 cities in terms of population and education levels and income levels and these things that we know are important to you. But, so you find them using Similarity Search, but we're actually way better than them in terms of crime. Maybe we're better than them in terms of the amount of people who do a particular type of shopping based on whatever market research we've done. So being able to find those places that are most similar and then compare yourself against things that maybe you're different than them in was another way that people were thinking about using Similarity Search. So there are a couple of ways that we decide what it means to be similar. One example is using attribute values. So essentially, we give you give us the attributes you're interested in, and the first thing that we do is we transform those variables. And the reason that we transform those variables is that so that we can compare apples to apples. If you think about it, if you gave us population and the percent of unemployment, population is such a big set of numbers. You're talking about thousands, tens of thousands, and percent unemployment is going to be a number less than 1. So the population is always going to win. It's always going to kind of show up as the most important variable unless we do this kind of transformation. So we divide the value by the mean, divide by the standard deviation, and that's called a simple z-transform. So if we look at some examples here, we have population, uninsured, and distance. And those are some very different kind of, the scale of those numbers are very different. So after we do our z-transform, we now have numbers that are kind of on the same scale, and we can compare orpals to orpals. So after we do that kind of standardization, essentially what we do is we subtract our candidate from the target. So each of those proposed store locations, their values get subtracted from our high-performing store. And so we find the distance for each variable, for each potential store location, we find the distance in data space to the store that's done really well. And we do that for each of those attributes. Then we square the differences so that whether it was higher or lower doesn't matter, it's just how far away it was in value. Like if it was 10,000 and 15,000 and 10,000 and 5,000, those are the same distance away. So if we square those distances, we want them to be the same. And then we sum those squares, and basically those locations that have the shortest distance in data space for each of those attributes becomes the most similar. It's very simple. From a kind of, we're just doing a bunch of subtraction and multiplication and calling it a day. But we can do some really powerful things with something so simple. One of the examples of an analysis that we did, this was with a colleague of ours named David Attaway. We looked at dengue fever risk in Kenya. And essentially what we had was known dengue fever locations. And we had 600,000 points across Kenya with attributes associated with them. And all we wanted to do was rank those 600,000 locations based on how similar they are to where dengue fever's already happened. Now, the traditional way to do something like this would be to do something like a weighted overlay, right? And we'd do that weighted overlay, and we'd say, okay, to create a risk map, we'd say dengue fever happens at a certain set of elevations, 2 miles away from the water source, with a certain amount of precipitation. But we know that mosquitoes don't fly around. They're leaving the river and they get 2 miles and they just, oh no, we've gone 2 miles. We can't go any further, right? These boundaries are fuzzy. And so by having to pick a hard boundary in something like a weighted overlay, we often kind of limit ourselves to these black and white boundaries that don't exist. And so what's cool about something like similarity search in this kind of risk analysis is that we're letting the data just speak for itself. We're not setting hard boundaries, we're letting the data kind of just show us where those boundaries are. And the next tool we're going to talk about is grouping analysis. Grouping analysis is all about creating groups so that within each group the features are as alike as possible, and between groups the features are as different as possible. So we're trying to create distinct groups in our data. So the output's a map. We can either constrain our map spatially so that we create groups that are contiguous. You do this if you were trying to create, let's say, sales regions, since you don't want to send a salesperson all over the place, right? They need to have a contiguous sales region. Or we can not constrain our analysis spatially. And when we don't constrain it spatially, what we often find is that we still see spatial patterns. So clearly this was not constrained, right? We have a chunk of green on one side, a chunk of green on the other, but we end up seeing that there are these spatial patterns, which is very interesting, and we'll kind of see an example of this in a minute. If you don't constrain it spatially, what we're using is a method called k-means plus clustering. It's a very, very popular clustering algorithm. It's not spatial. Of course, the output is a map, and you can see those spatial patterns, which is very interesting. But all it's doing is it's looking for groups in data space. It just sees the natural. We would all kind of see that natural two-group breakdown in this map, in this data set here, and it finds those groups. Now, if I said we're going to find a third group, where do we think that break would happen? Probably in that green, up and down, right? There looks to be a break there, and that's where that third group is going to be found by k-means clustering, or 4 groups. If you do choose to constrain your groups spatially, we use something called the minimum spanning tree in a method called scatter. And essentially what the minimum spanning tree does is it chooses these nodes and creates these links between those nodes and then cuts them down based on the constraints that we've set spatially and the distance between variables in terms of those variables that you've chosen. Now, if you don't understand one thing we talk about this whole time, it's probably going to be the minimum spanning tree, and that's totally okay, because the minimum spanning tree is super complicated and probably one of the most sophisticated things that I know our developer, it's like the thing he's most proud of ever building. So just know we're constraining those groups spatially, which does, of course, impact your results. You're never going to create groups that are as distinct when you constrain spatially as you would have when you create groups that aren't constrained, because then you're just letting it be all about the variables. When you force them to be spatial, it's going to do as good of a job as it can making them similar to each other, but it can't, you're still forcing this extra spatial constraint in there that will limit how good of a job it's going to do from an attribute standpoint. And of course, there is this report that gets created when you run grouping analysis. I'm sure you are all looking at that map of green, red, and blue saying, oh, I totally get that. No, it's just like a map of colors. It's not very useful until you interpret the results. Like, what is the green group? What does that green group represent? And I think the best way to understand what this report's all about is to see it in action. So Flora is going to show us an example of using grouping analysis.
Okay, so I have some data here about vulnerability in Africa from the CCAPS Foundation, and they look at some different factors, some different types of vulnerability, and they have indexes for these. So if I open the table here, we'll see that we have information about the population density, climate change, household resiliency, and governance index. And these are measures of how well the communities in these areas would be able to withstand a catastrophic event based on those 4 indices. And so I want to understand all 4 of those at the same time, because I could make 4 different maps and try to visually compare them, but grouping analysis helps us do a multivariate analysis and look at these variables at the same time. So I'll go ahead and point to my data set. And give it a unique ID. And give it another name. All right, so I'm going to split it into 4 groups. At the bottom of the tool here, we have an option to evaluate optimal number of groups, and that it gets included in the report. I've already done that. It takes a little bit of time, so I'm just going to go ahead and choose 4 and then choose our variables of interest. And I'm going to not constrain it spatially. And I will create the output report file because, like Lauren said, it's really hard. It's actually impossible to understand that map without the report. And I'm very creative with my report names. Okay. All right. Oh, I did it again. Sorry about that.
Patience is a virtue.
I'm looking at the clock, like we only have 15 minutes left.
We're okay.
We're better than yesterday.
We've lost time just now, though. Seconds we can never get back.
All right, now it's completed.
I've never seen that happen before. It's happened 4 times in the last 2 days.
I've never done it before. Okay, so we have the results here, and even before I open the report, we can see that although I did not constrain these spatially, there is a spatial pattern.
Geography matters.
Always. But to understand what this pattern is, we can look at this report. And so with these box plots, we can see how the different groups perform on these indices. So let's say, for example, the blue group. They have a really high score for vulnerability as related to household resiliency.
Which means they're more vulnerable.
Yeah, the higher the index, the more vulnerable. But they're a little bit lower in the population density. They're also the highest for governance index. The green group is really high for climate change, and that kind of makes sense since they're mostly coastal. So we see that spatial pattern even though they're not constrained. And we can target these places differently if we were going to try to do something about the vulnerability issue. We know that what people need maybe in the orange areas is going to be different than what people need in the blue areas. And that is grouping analysis.
And it's interesting to see that, you have areas in the northern parts of Africa and the southern parts of Africa that we would treat similarly, rather than just going in and kind of applying a blanket remediation effort. All right, so now we're getting into hotspot analysis. And we have a whole session right after this one about mapping clusters where we're going to get into a lot more depth about grouping analysis. We get into more depth about hotspot analysis. So we're going to quickly go through hotspot analysis, but we will you'll get a refresher on this and a lot more detail in the next section if you stay, because spatial stats are awesome. So hotspot analysis is all about finding where we have these clusters of high and low values. So let's say we have a set of Flora's favorite random numbers, which happen to be the digits of pi that she memorizes in her free time. Literally. So what if we picked those up and we threw them down and they landed like this, right? What we're doing when we run a hotspot analysis is we're asking the question, what are the chances that this happened randomly? Now, when we say this, what do we mean? It's really obvious in this case that basically all of the high numbers in that data set fell right next to each other. And it doesn't take a tool to tell me that that is really unlikely to have happened randomly, right? They all just happen to fall right next to each other. But the truth is that most of the time it's not quite that obvious. And so we use the tools to figure out what are the chances that these patterns that we're seeing are random. And if they're not random, then it gives us evidence that there is something going on under the hood, some sort of spatial process that we want to understand better. So the way that hotspot analysis works is you start with a feature, and each feature has a value, and each feature has a neighborhood. And we look at that neighborhood in relation to the entire study area. So the question is our neighborhood significantly different from our study area? That's what we're asking. And if it's significantly higher, then that feature gets marked as a hotspot. So if the neighborhood that that feature lies within has a significantly higher average than the study area's average, then it gets marked as a hotspot. And we go through and we do that over and over and over again, one by one, which luckily you don't have to watch. It just magically happens, and you end up looking at a map of hot and cold spots based on looking at the neighborhoods, comparing them to the study areas, and figuring out if they're hot and cold spots. So we're able to kind of do that. But one of the things that's very clear from understanding how hotspot analysis works is how critical that definition of a neighborhood is, right? That neighborhood is everything. And that neighborhood determines what your question is. So we're going to talk a little bit more about that in the next section, but one of the things that you can do to help you figure out what a good neighborhood size is, if you don't have a really kind of obvious one in mind, is use optimized hotspot analysis. Optimized hotspot analysis is a good place to start. It at least gives you an idea, like, hey, you might try this scale. And if it looks appropriate for what your question is, then you move on. You know, if you're looking for if you're looking for neighborhood level patterns, and you see, and the analysis that you're doing, let's say you have the state of California, and you're looking for neighborhood level patterns. You're not going to use a 50-kilometer neighborhood, right? Because you're not going to find neighborhood level patterns in a 50-kilometer neighborhood. So it's all about thinking about what your question is when it comes to that scale. There's no wrong scale to use. There's no wrong neighborhood to use. It's just does the neighborhood that you're choosing match the question that you're asking. And optimized hotspot analysis can help you with that. Now, in addition to optimized hotspot analysis and hotspot analysis in general, there's another tool called cluster and outlier analysis. And previously, we've not spent as much time talking about cluster and outlier analysis. So how many people in here have run hotspot analysis? How many people have run cluster and outlier analysis? Significantly less. I'll say every time I run hotspot analysis, I also run a cluster outlier analysis because they're both really powerful and they answer slightly different questions. So cluster and outlier analysis works similarly to hotspot analysis, except we have the feature, we have the study area without the feature, and we have the neighborhood without the feature, right? It's got a little donut hole in it now. And then we have the study area. And what we're doing is we're asking the question, is each feature significantly different from the other features? Is it higher or lower than the other features? And is each neighborhood significantly different from the other neighborhoods? And then we take that and we categorize each location. So if the feature is higher than the other features and the neighborhood's higher than the other neighborhoods, it's a high, high cluster. It's a hotspot. If the feature's lower than the other features and the neighborhood's lower than the other features, it's a low, low. It's a cold spot. But what's really exciting about cluster outlier are the outliers. So we have, if your feature's higher than the other features, but you're in a neighborhood that's lower than the other neighborhoods, then you're a high-low cluster. You're a high outlier. You are high even though you're in this low neighborhood. That's really interesting. Or you're low value surrounded by high values, and you're a low outlier. And finding those outliers is so interesting because there's no other way you could do it. If you think about it, these are not outliers from a data standpoint. It's not like if you sorted your table, these would be the biggest numbers and the smallest numbers. It's not what this is about. This is about those values that are different than their neighbors. It's a totally different question, and it's a really interesting question that you really need geography to answer. So we think that's kind of a underutilized tool, I would say. It's Flora's favorite. I like hotspot analysis and cluster outlier analysis equally.
That's not true.
That's not true. I love hotspot analysis. I do. Cluster outlier is awesome too.
I think that we're going to be demoing these the next workshop right after this one, so in the interest of time.
Yeah. So in addition to those, we also have some new tools that do space that are both spatial and temporal. Instead of just defining neighborhoods in space, imagine defining those neighborhoods in both space and time. So it's saying that I'm more related to something that's close to me spatially and temporally than I am to something that's just close to me spatially. So if I'm a protest and I happen at this location today, I'm probably more related to a protest that happened a half a mile away yesterday than I am to a protest that happened in this exact same spot a year ago, right? The protest that happened yesterday is totally more relevant to me. It's more probably related than I am to the one that happened a year ago in the same location. So taking into account both spatial and temporal relationships is crucial, and that's what these tools are all about. And there's two tools to do this. One is the Create Spacetime Cube tool, which essentially aggregates your data into a spacetime cube, binning it in space and time. And then we run on top of that an emerging hotspot analysis, which does a spatial and temporal hotspot analysis, defining neighbors in space and time. And then in addition to just finding out where we have statistically significant hot and cold spots, it actually categorizes each location based on their spatial and temporal, the temporal trend of hot spots or cold spots in that location. We'll talk a lot more. I could talk about that like for an hour and a half. So I'm not going to do that now, I promise. But really powerful tools for kind of bringing your analysis to the next level, bringing that temporal aspect of your data kind of into the mix instead of just what we've kind of been limited to before, which is snapshots. You know, we look at January, then we look at February, then we look at March when we have temporal data. But now we're bringing it all in together and actually integrating it into the analysis. Now, we've talked a lot about where are the hot spots, where are the cold spots, where are the trends, where are the outliers. But we also have tools that help us answer why questions. And these why questions are often answered using things like regression analysis. And so we do have some tools that allow you to do that kind of work. In addition to regression analysis, the Modeling Spatial Relationships Toolbox also has some tools that help you figure out how neighborhood sizes are determined. And we're going to talk a lot more about that, but you're not limited to just distances. You can also go by the number of neighbors. So we can say 4 nearest neighbors. I know this is Flora's favorite conceptualization. We can also define neighborhoods using networks and actually define the distance. Instead of it being 10 kilometers as the crow flies, it's 10 kilometers along a network. Now, in order for these tools to work, you need to have network analysts, because we're taking advantage of we did not reinvent the wheel just for this tool. We're just using functionality that exists in Network Analyst. And you also need a network data set, right? But this can be a very powerful way of kind of defining neighborhoods. And then we have our regression analysis tools, and we do a whole workshop about regression analysis, and we're going to do that tomorrow morning is our regression analysis workshop. But we have ordinary least squares regression. We have a very powerful kind of exploratory regression tool that is an implementation of ordinary least squares regression that lets you explore correlations and combinations of variables in your data. And then we have geographically weighted regression, which is super spatial and really awesome and essentially gives you equations for every feature in your data set and really allows you to see how relationships vary across space, which is very powerful if you're talking about being able to focus remediation efforts. And you're really able to make a lot of different kinds of maps that help you understand the relationships that exist in your data. And we'll talk a lot about that in the session tomorrow morning. So with that, we do have time for questions. And I do want to point you to esriurl.com/spatialstats. That has tutorials with hands-on data and step-by-step instructions. We've got videos that have our workshops from last year. As soon as these workshops are recorded and we get them, we'll put up the latest workshops. Tons of resources there. We also have the rest of our sessions. We've got one more today about cluster analysis and then 2 more tomorrow. The list is whittling down. We started with 8. And we also would beg of you to please fill out a survey. We really do read the surveys. They're very important to us. We love to get your feedback. Of course, we've already given the feedback. We could use a bigger room, but it can't hurt to come from you guys. And just in general, we love to hear from you. It means a lot to us. And thank you very much. And we have time for questions. A little bit of time for questions, but time.
3 minutes.
Nonetheless, time.